Good evening, everyone. Myself Gautam Sharma. I welcome you all in a Sapience Education. For more details, you can visit our website www.sapienceeducation.com. So today I'm going to discuss about the following topics. We have thermal, especially thermal expansion, linear expansion, area expansion. This chapter comes under the thermal properties of the matter. So first of all, I will go for what is thermal expansion. After that, I will go for linear expansion, area expansion, volumetric expansion, and relation between thermal coefficient of thermal expansion. So how many topics I am going to discuss? 1 2 3 4 and 5 as well, right? So 5 topic I will discuss in this video. And I think you have understood now what is expansion means. Extent, when we apply a heat in any matter, so what, how it behave. Okay, this chapter is all about thermal properties of a matter. So let us consider there is a matter like this rod. Okay, and if you heat this, then what will happen? So it will definitely try to change its shape and size. So how this behaves, so we need to discuss each and everything step by step. From figure you can understand here that from figure, let us consider this was the earlier stage of the rod. Now after applying a heat, what happens? After applying a heat, we see that rod gains its new position, that is its length become new length, that is length is an extension form, right? So there is an expansion form, and if you cool it, so definitely it will shrink. So there is a shape change in a shape and size. So thermal expansion is it, the word itself says you that there is an expansion of the object when we put a thermal energy. So whenever you will put any thermal energy to any matter, so it will try to expand it. So this is the natural behavior of most of the 99% material, right? So let us consider define. So if you go for definition, so definitely you will able to understand that the increase in a dimension of a body, it may be length, it may be area, it may be volume. So increase in the dimension of body due to increase in the temperature is called thermal expansion. I hope, I don't think it require more elaboration. Now let us consider thermal expansion of a solid are of a three type. How many types are there? So definitely there are three types are of a thermal expansions are there. So I will discuss each and every types more elaborative manner. Okay. So let us consider a linear expansion. Okay, what is actually linear expansion? Linear. So linear means what? Length. When we are talking about length, so we are considering as a linear expansion. Okay, so it is the increase in the length. So when suppose there is a in there is a length L naught, that is your initial length, and when we heat, what will happen? It will try to expand. So this is known as linear expansion. There is a change in length. Okay, length increases other as compared to the other dimension, that is area and volume. Mostly we will look after the length only. So this type of expansion is called linear expansion. So L for linear and L for length. So when we talk about the expansion of expansion in a length, so we consider this as a linear expansion. So I hope you have understood now. Now let us see how linear expansion happens. See, I hope you have see here when we apply a heat. So what is happening here? See, try to understand. Focus here. So when you apply a heat, so what will happen? Due to heat, there is an expansion, and when there is an expansion of rod, earlier see here, earlier this was a position. Now see from the mark, this was a earlier position. As you heat, so the length of the rod increases, and this increase in the length is known as linear expansion. So have you understood now what is actually linear expansion? Increase in the length. Okay, what is linear expansion? Increase in the length after applying a thermal energy. Got it? Now let us derive some of the formula so that we will able to figure out and we will able to solve some of the numerical. Okay, now step by step you go. Okay, let L naught, first of all we consider this as L naught as original length of the object. So this is your original length, this is your original length in the blue color. So this is the original length, that is L naught. Okay, now after application of heat, what will happen? After application of heat, after heat is being applied, heat is being applied, what will happen? What will happen? Its length increase. So earlier it has length L naught, and final length is your final length is your L. Okay, final length is your L. Okay. Now, as you see from figure, so when there is an expansion in the length, so how much change is in length happen? So delta L is your change in length. Okay, delta L is your change in length. How much change in length happen? Delta L. So can we tell that delta L as L minus L naught? Because L was final length and L naught was initial length. So can we write change in length as L minus L naught? Okay. Now T naught is your initial temperature and T is the final temperature. Initially the temperature was T naught and finally it was a temperature T. So if you talk about change in a temperature, so how you will do? So definitely final temperature minus initial temperature, and this is known as change in a temperature. This is known as change in a temperature. I hope so. Okay. So you have understood now change in a temperature delta T, change in length delta L. Okay. Now we know that change in length depends upon length L naught. How? The more the object length is there, so more its expansion will be there. Suppose this is your 1 meter and this is your 2 meter. Two rods are there and it has a length of 2 meter. Okay. Now if we will apply a heat, so what will happen? If I will apply a heat, so what will happen? So it has some extension, and this object has also some extension. But practically when we see that as much as length, original length was more, the more expansion it has happened. It means that change in length is directly proportional to the initial length. The more you have initial length, the more change in length happen. And if less you have a initial length, so less change in length will happen. So this was the first condition we have seen. Okay, I hope you have understood this. Okay, I hope you have understood this, right? So it means that change in length depend upon the original length. More is the original length, more is your change in length. So this is your directly proportional. So whatever I am talking about, this only, this equation only. I hope you have understood this equation at all. Now it has been seen that change in length is directly proportional to the temperature difference. More is the temperature difference, more is the change in length. For example, let us consider earlier it has temperature of 100 degrees Celsius and outer temperature is your 25 degrees Celsius. So difference is, or we can also tell like this. We can also tell that earlier it has temperature of, earlier, let us see here. Earlier it has temperature of T is equal to 50 and final temperature T final, T naught was 50 and T final is equal to 100. So the length has been changed. Now if I will tell that no, this final temperature is your 200. So if the final temperature is 200, so the difference is very high. So as you increase more and more, that is change in temperature is more, so the length of the extension or the linear expansion is more. It means that change in length is directly proportional to the temperature difference. More your temperature difference will be, the more your length will increase. So basically if you combine all these two equations, so what you will get? So the equation number 1 as well as equation number 2, if you will combine this, then what will happen? What will happen? So if equation number 1 and equation number 2, you will combine, so you will get that change in length is directly proportional to the original length as well as change in temperature. Okay, so I hope you have, this is clear now. I hope this is clear now. Okay, now going to the next step. If change in length is directly proportional to the original length as well as change in temperature, so if you remove this proportionality constant, so you will get sum of the constant, and this proportionality constant, it is also known as coefficient of linear expansion. It is known as coefficient of linear expansion. Okay, and this is your proportionality constant. Now tell me, We have earlier studied that change in length is equal to what? Change in length is equal to L minus L naught. Okay. So here I have given change in length as L minus L naught in place of this, right? Alpha in place of alpha I have written L naught, I have written L naught. Now tell me what is change in a temperature. So definitely if you go for change in temperature, so put this value. So when we put this value, change in temperature as T minus T naught, and finally we will get that L naught will come this side, so plus alpha into L naught T minus T naught. So finally, if you take L naught as a common, so finally you are getting L is equal to L naught 1 plus alpha T minus T naught, where alpha is your coefficient of thermal expansion. Okay. So I hope you have understood this phenomena, right? I hope you have understood this linear expansion, right? So numerical will be basic numerical in numerical they will give all the values except one. They will give maybe they will give linear expansion, maybe they will give initial temperature, final temperature, initial length. You need to find final length, or you may want to find change in length, then you can easily find change in a length. Okay, so these are the thing. Got it? I hope you have I hope you have understood now, right? Okay. So it is very easy for easy one. So you need to understand, for shortcut you need to understand this formula only, okay? Because you know all the other thing. So don't go for so much expansion. You can do it by yourself. So for example, change in length is equal to alpha, that is coefficient of thermal expansion, into original length L naught into change in temperature. You can write here change in length is equal to L minus L naught. You can write it by change in temperature is equal to T minus T naught. So don't mug up all these equations so that it may complicate you. So you go for a simpler one, okay? So I hope you will able to solve mostly problem by this equation only, right? So don't go for this just mugging up these things. Okay, you need to understand the derivation. If you understand this very simple derivation, I don't think you will get any type of difficult questions at all. Okay, so this will, for board exam at least you will able to solve each and every problem, right? Now let us go for now linear expansion. We have completed, right? We have completed this expansion. We have talked about linear expansion. So thermal expansion completed, linear expansion is completed. Now I will go for areal expansion. What is areal? Area of expansion. When there is an expansion, superficial expansion, it is also known as superficial expansion. Okay, so let us consider here. So this is your area, right? This is your area, this is your area, or you can say that aerial plate, circular plate, anything, any plate like structure, thin plate like structures are there like this. Okay, now if you increase the temperature, if you heat this body, so what will happen? It will try to expand, it will try to expand in all direction at all. So basically it won't expand in the thickness because its thickness is very small, but in side by side it will increase. So if this is your initial point and this is your final point, so from figure what you observe, what do you observe? So it was initially a naught, area was a naught, but as you have increased temperature from T naught to T naught plus delta T, so what happened? What happened? Your area got changed from A naught to A naught plus delta area. So see here, area has been expanded. That portion has been expanded extra, right? So this is change in area, right? This is change in area. I hope you have understood. Okay. Now we will go for the derivation part. So increase in surface area while heating a solid is called as superficial expansion or aerial expansion as well. Okay, so I hope you have understood now. Now tell me, change in area depends upon the initial area. The more area it has initial, the more change in area will happen. So this is the first equation. This is your first equation, right? This is your first equation, I hope. So So this is your equation number 1. Now change in temperature. The more you change in temperature, suppose there was 20 degree earlier, it has 20 degrees Celsius. Now you have increased from 20 degree to 100 degrees Celsius. Now in second case you have increased from 20 degree to 200 Celsius. So if you are changing only 80 degree Celsius and here you are increasing 180 degree Celsius, so the more expansion will be here. So the more change in temperature, more expansion will be there. If you heat more, so more change in expansion will happen, right? So it means that expansion in area is directly proportional to the change in temperature at all. I hope you have understood now. Now, if you combine this, then you will get change in area is proportional to the initial area into change in temperature. Now you remove this. What? You have to remove this proportionality. So if you want to remove the proportionality, you need to give some constant, and this constant is called beta. This constant is called beta, and this is known as coefficient of superficial expansion or the coefficient of areal expansion. Okay, so I hope this formula is very much sufficient. You need to remember this formula only. Now for solution purpose, so for solution purpose, let us see here. It is very easy to write. So here you want to find a change in area. So change in area is equal to final area minus initial area. That's it. And this is equal to beta into change in area is a naught into change in temperature is equal to initial temperature minus final temperature. Now standardize this equation. This is very simple. So only you need to remember this, and after that you have to apply your basic logic, so that you will able to solve different type of problem. I will come to the numerical part in separate video. For that you need to wait, or you go and subscribe our channel, so that you will get regular update about the numericals and all. I will explain it properly. So I hope you have understood now area of a superficial expansion, right? Now can we go for next topic, that is your volume expansion. Now earlier what you have studied linear expansion. So lengthwise expansion is your linear expansion. After that you have got areal expansion, area wise expansion. Now I am talking about volume. So increase in a volume of a solid on heating is called volume expansion. So when you increase the temperature of a volume solid body, so what will happen? Its expansion, volumetric expansion will happen. Means everywhere, every side, every length will expand. It means that there is a change in a volume. So let us consider there is an initial volume that is known as volume that is known as V naught. Okay. So see here, initial volume was V naught. What is final volume? So earlier it was V naught and final volume was V. So change in volume can be written as V minus V naught. Okay, now initially it has temperature of T naught, and after heating you have got final temperature as T. So can we write here change in temperature is equal to T minus T naught. Now same thing, change in volume depend upon its initial volume V naught. So it will be V naught only, right? Not V. So it is your V naught. So change in volume is equal to initial volume. Change in a volume is proportional to initial volume. So the more initial volume it has, more change in a volume will happen. And if it has less change initial volume, so less change in a volume will happen. So it means that change in a volume is directly proportional to the initial volume. Another important thing is your change in a volume is directly proportional to the temperature difference. Now if you combine this both equations, so what you will get? So definitely you will write here, definitely you will get like this: change in a volume is directly proportional to initial volume V naught into delta T, right? And if you remove this proportionality constant, so you can write here change in volume is equal to proportionality constant, that is gamma into V naught into delta T. So what is gamma? Gamma is your constant of proportionality is still, it is called the coefficient of volumetric expansion. So see here, as we have earlier discussed, that change in a volume is directly proportional to V naught and delta T. So here we have written change in a volume is equal to uh, here in some book they will use alpha volumetric, or in some book they will use gamma. So here in NCERT I have seen here that they have used alpha. So you can write here alpha into volume. You need to use this symbol alpha into volume, right? So alpha volume means what? Volumetric, coefficient of volumetric expansion. Okay, and it is also considered as gamma also. So you can also write here gamma is equal to alpha volume, alpha V or gamma. Okay, so some book has different thing, different symbol, and some book has different symbol. So here we can now use this only. You should remember this formula only. Okay, so it's here, it is how easier. So here it has initial volume B minus final volume minus initial volume is equal to alpha V into V naught T minus T naught. Okay, now here we can write here V is equal to V naught 1 plus alpha V T minus T naught, right? So how many you have got, how many coefficient of expansion? That is your alpha, that is length, coefficient of thermal expansion, linear expansion. Beta is your coefficient of areal expansion, and gamma, that is, or alpha V, that is your volumetric coefficient of volumetric expansion. Now there is a relation between alpha, beta and gamma, or you can see. So generally you will get that alpha is equal to beta by 2 and alpha is equal to gamma by 2, or beta is equal to 2 alpha you can write, and volumetric volumetric coefficient is equal to 3 into alpha, right? So how you will prove this? How you will prove this? Okay, it is a big question, that how you will prove this. Let us see here. Let us consider superficial expansion. Okay, I will derive it, what that relation. Okay, so let us consider superficial expansion or areal expansion. So area is equal to length into length. So earlier area was what? Earlier A naught is equal to L square, and finally when after hitting its length become L plus delta L, right? So earlier it has area as L square, and final area is L plus delta L whole square. So can we tell here change in area is equal to L plus del L whole square minus initial area? So simple. Now please expand this. So A plus B whole square will be equal to L square plus delta L square plus 2L into delta L minus L square. So L square all cancel. Since delta is already, change in length is small, so its square will be very small. So can we ignore this? Can we ignore this? So definitely we can ignore this. So finally you can write here 2 into L into delta L. Now I will multiply and divide by L. So what you are getting? So L into L will be L square. See here, 2 into delta L into L square divided by L. So L square means what? Area, initial area. So change in area divided by initial area. Why I am writing here? So I hope you are understanding here. See, let us explain you a bit proper way. See, it is your 2L into delta L into multiply it L by L and divide it by L. So finally you will get 2 into change in length by L into L square. Now what we have considered area as L square, that is initial area. So here area can be write here 2 into change in length by length into area. So can we make this area downside? So change in area divided by area is equal to 2 into change in length by original length. Now tell me change in area by area is equal to what? That is initial area. I am talking about initial length. So now tell me, what is change in area by original area, right? Now remember this equation, change in area by original area. Let us see here. So can we write from here change in area by original area from this equation? Change in area by original area, that is a naught, is equal to beta into delta t. Can we write this? Similarly, change in change in length by original length is equal to alpha into delta t. So use this equation, both equation, right? So here we can write here change in area by original area is equal to beta into delta t. Change in length by original length is equal to alpha into delta t. So delta t got cancelled. So finally we have got beta is equal to 2 alpha. So this is what we are discussing about, that we have got relation beta is equal to 2 alpha. Okay, so this is the process where you will able to derive this, right? So in this way you can derive this type of equation. Okay, now let us go for a volumetric derivation of a volumetric expansion. Okay, let us consider earlier it has length l naught only. Okay, you considered it as l naught. Initial length was l naught and final length was L plus del L or L naught plus del L. Okay, no issue at all. Or you can also tell like that initially it was L and finally it was L plus del S. So initial volume, this was your initial volume P initial, and this is not your initial volume. Okay, sorry. Okay, yeah, this was final volume and this was initial volume. Why? Because if you consider this length, so this is your L and L. So volume, if you want to find volume, so it has initial volume L cube. And what is the final volume? So final volume, so when it expanded, so it has length L plus del L, it has length L plus del L, everywhere L plus del L. So every side you have got L plus del L, right? So final volume will be L plus del L whole cube. So final volume minus initial volume, if you will do this subtraction, so what you will get? So please expand it. So when you expand it, L cube plus del L cube, that is A cube plus B, A plus B whole cube is equal to, you know this formula, A cube plus B cube is equal to A cube plus B cube plus 3AB A plus B, right? Or 3A square B and 3AB square, right? So here what we have done, see here, try to understand. I have expanded it. Okay, I have expanded it like L cube plus del L cube plus 3A square, that is L square into delta L, plus 3A into B square, that is 3A into B square minus L cube. So L cube got cancelled, and small delta L cube as well as delta L whole square is approximately equal to 0. By why? Because it is very small, and if it is your very small, then what we will get? We will finally get it is as a 0. It tends to be 0 because L is it is not a 0. It is not a 0. See, it is not a 0 because this will be 0 because change in length whole square can be considered as 0. So finally you are getting 3L square into delta L. So 3L square into delta L, again I am multiplying it by L, divide it by L. So finally what we are getting here, 3L cube, see here L square into L, that is equal to 3L cube into delta L by L. Okay, now tell me, L cube we have considered as a volume. So change in volume by original volume can be written as 3 into change in length by original length. Now remember same thing, change in volume by original volume is equal to coefficient of volume expansion into change in temperature, that is equal to 3 into alpha L into delta T, right? And this you have got cancelled, so finally you have got relation alpha B is equal to 3 into alpha linear expansion. So alpha volumetric expansion is equal to 3 times linear expansion. So this is the final formula. So I hope you have understood that why we have come to this relation. So this relation has been proved. So I hope you have understood now. So by using that relation, you can solve so many numericals at all. Now, one more important thing where I'm going to focus here. So, as you know that change in volume is equal to alpha V into V naught into delta T. So, it has been seen that alpha V is equal to change in volume by V naught into delta T. So, here what we can write, change in volume by original volume into 1 by alpha delta T. Okay. So, it has been seen that by experimentally, although delta V is a constant, but if temperature has been changed, if you will change, increase or decrease temperature, so it will change, but it will not in the case of alpha, it will won't be the case of beta, it will be only the case of gamma only. So here we can see that coefficient of volume expansion for a copper. See here, coefficient of a volume expansion for a copper as a function of temperature. So if you see here, temperature increase in this step, alpha volumetric is behavior. Okay. So this is the alpha b value, right? So here you can see alpha volume or volumetric expansion of aluminum. Coefficient of volumetric expansion for aluminum is 7 into 10 power minus 5 per Kelvin. Brass, iron, paraffin, glass. So it has more in alcohol, less in aluminum. Okay. So I hope you have understood this. So for now it's okay, and I will solve numerical in separate videos. Thank you for much. If you want more and more numerical solution and all and next chapter, so please subscribe that, so that you will able to get regular updates of these videos and all. Okay, thank you everyone.